Thank you very much, and thank you for joining this tribute to Rosalind Franklin, which was supposed to be 100 years on, but actually is 101 years on, and actually today would have been her 101st birthday, so we're perfectly timed on that. So I'm going to run through her early life and give pointers to the other 5 talks in the session, which are about the coal, DNA, and viruses. So I'll introduce her early life, and then and at the end I'll just say what the next 100 years might bring if we look in our crystal ball. So sorry, this is not the birthday, it was last week, I got that wrong. It's the 25th, sorry, the 25th of July. I read a post today which was obviously a week old. Anyway, she was born in London. Her parents were Muriel and Ellis Franklin. She had an older brother, David, and 2 younger brothers, Colin and Roland, and then a very much younger sister. You can see on the left here the picture of all the brothers and sisters. I'm just going to put a pointer up here so that you can see. There's Jennifer Glynn, who amazingly is still alive, living in Cambridge, and wrote a wonderful book about Rosalind Franklin called My Sister Rosalind, which I commend to you. She very early on, even age 6, showed her academic prowess, and her Aunt Mummy, after a holiday in Cornwall with the family, said, Rosalind is alarmingly clever. She spends her time doing arithmetic for pleasure and invariably gets her sums right. When she was 9, she was sent off to boarding school at Bexhill-on-Sea, but then at age 12, she came back to St. Paul's School, girls' school, in London as a day girl. The High Mistress there has a wonderful quote, which from this time, 1932, I think should be right, which is that the High Mistress considers that no woman has a right to exist who does not live a useful life. Make beyond marriage as your goal. Sorry, I actually can't read because look beyond marriage as your goal. So she excelled at both sport and in all her studies. And when she was 16, her mother is quoted as saying that all her life, Rosalind knew exactly where she was going. And at 16, she took science as her subject. All her life, it came straight from the heart. So this is what she really, really wanted to do. In the summer of 1938, as a school leaver, she went to Paris, and this is where she fell in love with the French people, the French food, everything French, plus hiking and mountains, because she hadn't really experienced mountains in the UK. She then went up to Newnham College, Cambridge, in 1938, and read natural sciences with a specialism in chemistry. And she had a bicycle, and she used to ride home to see her parents in London. She thought nothing of doing this 65 miles, 105 kilometers just to ride home to see them. In the first year, she was second in all of the prelims, in the whole year group in her first year exams. And she did a final year research project with Fred Dainton, who became Lord Fred Dainton, who was a photo and polymer chemist, and that went very, very well, and she really, really enjoyed it. Then Newnham College gave her, this is just a page from her notebook from the second year, from the autumn of 1939, which shows her learning about crystal physics and space groups and various crystal forms. So Newnham College gave her a 4th year scholarship. And she had a very, very bad-tempered and autocratic supervisor called Norrish, RGW Norrish, who found her very hard to deal with because she didn't suffer fools gladly. And he found that confrontation when cornered was her tactic. And they really, really didn't get on. And she was very claustrophobic. She was put in a small dark room and given a really impossible project. And she didn't like that at all. However, she finished her degree, but in Cambridge, women could not be awarded degrees until 1947. I just wanted to point out that I actually work in Oxford, and they gave women degrees in 1921. So we were 26 years ahead of Cambridge in that. That's a shield of Cambridge University here. She did actually get that degree in 1947, but not till then. So she had to wait 5 years for it. She then registered at Cambridge as a PhD student, but she actually worked for BCURA, which stands for British Coal Utilisation Research Association, which is quite a mouthful. and she worked on the permeability and shrinking of coals when you put them in gas and when you put them in water as a function of temperature. She was based in Kingston in West London, and her title was Assistant Research Officer. This was during World War II, 42 to 45, and she was an air raid warden in the evenings and nighttime. And so she submitted her thesis in 1945, and that the title was The Physical Chemistry of Solid Organic Colloids with special reference to coal and related materials. In 1946, her very first paper was published. That was in the Transactions of the Faraday Society, and her hypothesis was put forward about molecular sieves. And this turned out to be very, very important research directed to making better gas masks, because what these graphite powders did when they were wet and when gas came in, it's a very important part of that. She then went to Paris as a postdoc from 1947 to 51, so revisiting her beloved Paris, and worked on coal and graphite under Jacques Marin, and he was trained by Lawrence Bragg at the Royal Institution. She was in a government laboratory, and she got un-Englished, which I think is a lovely way to put it, but she really became a total Francophile. She was paid £5 a week, and her rent was £3 a month. I just thought that might put the money in perspective. What she loved about working there in Paris, and it horribly contrasted with what happened to her when she came back to the UK, was that in Paris, she said women were engaged as equals, not as subsidiary or underdogs, as it were. So then she went to King's College and worked on DNA. We'll hear about that in a minute. And then finally, her last 5 years, she was at Birkbeck College under the good offices of Sage Bernal, who was extremely supportive of her. And that can't be said of Randall, who she was under at King's College. So the coal and graphite part of the story, this is just her first paper that I already mentioned, received in 1946. I'm not going to go into the science at all, because we're going to hear about that from other people. And the first paper that we're going to hear is about her observation of aromatic bond density. Now, this is very important. It was in Nature in 1950, and it basically was a new description of the covalent bond. And we'll hear Alexander Nazarenko is going to, from sunny Buffalo State, is going to tell us about that. Then we're going to hear about the structure of graphitic carbons, the studies she did as a PhD student, and then continued in the same sort of work, but more crystallography in Paris from Margaret Schott. And then thirdly, we will hear from Thomas Fitzgibbons, who's from the Dow Chemical Company, about how what her research on carbon-based materials still governs and guides, still guides the development of new materials. And I think it's a real shame that her work on coal is actually not at all recognized. You know, she just seems to be known for those 2 years at King's for the DNA, when in fact she made absolutely critical contributions to 3 areas of science, which is coal, DNA, and then viruses. So the DNA story is going to be told to us by Professor Brian Sutton from King's College, and she ended up going there because Charles Coulson at King's advised her that if you're interested in possible biological applications of the technique, meaning crystallography, that you know so well, there could be a lot to be said in favour of King's. And then her response to this, to Coulson, was, I am, of course, most ignorant about all things biological, but I imagine most X-ray people start that way. I love this quote because I was trained as a nuclear physicist, and I definitely started out most ignorant about all things biological. But it turns out that physicists, Rosalind Franklin, as a chemist, have much to contribute to this field. So in order to get to King's College, she won a 3-year Turner and Newell Fellowship, which was under Randall. And this fellowship was named to be working on proteins in solution and changes in structure when they're denatured, when they're heated or dehydrated. But during the negotiations for this fellowship, Maurice Wilkins at King's had got some DNA fibers from Rudolf Signer in Bern, and in May 1950, and Randall suddenly changed Rosalind Franklin's project to look at these DNA fibers. And this famous photograph, and I know that Brian is going to tell us all about this, and I don't want to take his thunder, but I did want to point out that if we were together, you'd actually see that people commercially have made money from this photograph too. And this is my skirt, which has photograph 51 all over it, the fiber diffraction pattern of bDNA. And this very, very famous photograph taken by Ray Gosling, who was a research student of Wilkins, but actually was working with Franklin. And we're going to hear the ins and outs of this story after the break from Brian Sutton. So that brings me on to the third of her amazing contributions, which is viruses. And she moved, as I said, to Birkbeck College for the last 5 years of her life, which was cut all too short. She was only 37 when she died of ovarian cancer. And she famously quoted that she had a fifth floor office of a bomb damaged site, a bomb damaged house at Birkbeck, and she had swapped a palace for a slum. However, she loved that slum. The X-ray lab was in the basement. It leaked. You had to have an umbrella when you were doing experiments because water actually came through the ceiling onto the equipment. And she got funding independently as a senior researcher from the Agricultural Research Council. The first virus ever identified was tobacco mosaic virus, and she actually got the structure of that. And the crystals you can see up on the right here, and this is her office on the fifth floor of that bomb damaged house. So she was under John Bernal, or Sage as he was known, and he thought the world of her. He protected her, supported her, and made a very, very happy environment, and quoted her as a brilliant experimentalist. And I like this quote from him: "As a scientist, Miss Franklin was distinguished by extreme clarity and perfection in everything she undertook. Her photographs are among the most beautiful X-ray photographs of any substance ever taken." Can't say better than that. We're going to hear about that from Gerald Stubbs and also from Joseph Orgel about the structural biology that she did at the end of her life. So what have been the developments in the last 50 years in protein crystallography, which has made virus crystallography so much easier, or rather so much more tractable, I should say? Well, we can now grow up our proteins in E. coli. So the molecular biology revolution has allowed us to produce any protein we like by expression. We can use crystallization robots to try and crystallize our proteins, and we can set up thousands of conditions with small volumes of protein to try and get crystals, because we still don't understand exactly how they grow or why they grow. We've got synchrotron radiation, which is parallel, so that we can look at viruses which have very large unit cells, and we can separate the spots of those, because we've got no divergence or convergence in our X-ray beam. With very high flux densities, and pivotally we can also adjust the energy of the incident X-rays, so we can excite absorption edges. We've got cryocrystallography, which allows our crystals to last around about approximately 70 times longer in the beam than at room temperature. We've got selenomethionine derivatives so that we can do our phasing, although as you'll see in a minute, it's possible we don't need to phase protein structures anymore. We'll do them all by molecular replacement from alpha fold 2 structures. We've got huge position sensitive detectors, which have really revolutionized in terms of speed and the size of the diffraction pattern, the extent of a diffraction pattern that we can detect, and incredibly powerful computers and also computer software for crystallography. So all of these things have actually contributed to the revolution in structural biology and allowed us to find structures of whole viruses. So this is foot and mouth disease virus. As I said, the first one was tobacco mosaic virus, and this is blue tongue virus. Both of these came from Dave Stewart's group in Oxford, which is why I like to show them. But blue tongue virus in particular is enormous. So would Rosalind Franklin have got a Nobel Prize had she lived. And this is a rather contentious and debated subject, and possibly Brian will touch on this as well. The Nobel Prize can be awarded to a maximum of 3 people. It is not awarded posthumously, and so the 3 people that received it in 1962, the Physiology and Medicine Nobel Prize, were Francis Crick, James Watson, who built the model, and Maurice Wilkins, who was an experimental scientist working at King's as well. And so the question is, would she have got it? Well, there's been a huge amount of posthumous recognition. Probably at the time she wouldn't have done, because she was a woman, to be honest. There's been a lot of recognition now of her. There's a King's College Franklin Wilkins building. There's a Rosalind Franklin University of Medicine and Science University in, sorry, that's twice, in Chicago, Illinois. There's a blue plaque where she lived, and here in London, and in Union College, Cambridge, there is a statue of her. But I meant to take that out because her sister, Jennifer Glynn, doesn't, not too keen on that statue. But they have also named one of the graduate colleges after, graduate accommodation blocks at Newnham after her. If you look on Wikipedia, there's 39 listed memorials of her, and the special architectural and historical interest is her tomb. And on the tomb, it says Rosalind Elsie Franklin, and then there is some Hebrew and her parentage, and it said scientist, that's her profession. Her research and discovery on viruses remains of lasting benefit to mankind. So what's very interesting is that there's nothing about DNA on the tombstone. I just picked out 3 other memorials to her. One of them, or rather tributes to her, one of them is the Rosalind Franklin Institute at Diamond Light Source, which is a medical research centre. And this is a joint venture of 10 universities funded by the UK Research and Innovation organisation, and it's been launched at the Harwell campus. And in 2019, the European Space Agency named their ExoMars rover the Rosalind Franklin. But my favourite is that in 2019, on the 2nd of September, the University of Portsmouth announced that it was changing the name of James Button Halls to Rosalind Franklin Halls. And I think that that says a lot about the new view of her contribution to the DNA story. There's some wonderful things about her. There's a book here about 50 fearless pioneers who changed the world, and women in science, and she's one of them, with this picture of her, which mentions cold, double helix and viruses there. And this is the page about her, and I rather like all the little cartoons around it. So 1 minute on the future, what's going to happen in the next 100 years? We've got lots and lots of 3-dimensional protein structures. We need to find what their function is. We need to find lots more membrane protein crystal structures, because there's still much to learn there. We can maybe one day do single particle imaging of whole protein molecules with free electron lasers. Bioinformatics, certainly the algorithms are becoming more and more powerful because of our modern computing power available. And a new child on the block is AlphaFold 2, where 350,000 predicted structures have just been uploaded by the EBI and the DeepMind team, so that they've taken lots and lots of proteins and predicted their structures, so that you could probably use those for molecular replacement to solve your structure rather than having to do the phasing. However, there's a feeling that this will be much trickier for large protein complexes, and we'll still need to actually do the experiments for that. And of course, we've got electron microscopy, which is now coming up and determining a lot of high resolution structures. So that's my time up, and thank you very much for listening to me, and I'm really looking forward to the other 5 talks, which will go into more depth of what I've merely skimmed over.